Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about how we know what elements are in the stars. And in order to talk about that, we're going to need to talk about the emission and absorption spectra of different elements. So let's get into this. So how do we know which stars have which elements? Well, we can analyze the wavelengths of light that are absorbed or released by the stars themselves. And so what this means is that depending on what elements are in a particular star, different wavelengths of light are absorbed or released from the stars. And so if we can detect that and see which bands of light or which wavelengths of light are absorbed or released by the stars, we can then indicate what elements must be in there to give us that result. Okay. So before we get into that, we need to talk about what's happening in the atom, right? What's happening in the atom when you get this absorption or release of energy. And so what we need to focus on are the electrons. So when you put energy into the atoms of a substance, it's the electrons that are going to pick up some of that energy. And so if you give the atom energy, the electrons can absorb that energy, and then they go up to a higher energy level. So if you remember from a previous video, we talked about how the energy of the electron is associated with the energy levels that it's at. And so the electrons tend to be at lower energies, and they're going to be closer to the nucleus, so they're going to be down lower, right? But if they absorb some energy, then that's going to kick them up to a higher energy level. They're going to then be farther away from the nucleus. So in the beginning, we can see that this electron here is in the lowest energy state possible. So we call that the ground state. And so when we put the energy into the electron, when the electron absorbs energy, it then jumps up to a higher energy level, and we call that the excited state. So think about an analogy is like when you get excited, that means that you have energy, okay? So the electron absorbs energy, jumps up to a higher energy state called the excited state. Ground state to excited state. So this is very much like you climbing a ladder, right? So again, when you're closer to the ground, you have a lower gravitational potential energy. But as you climb up to higher rungs on the ladder, your gravitational potential energy increases. Same thing for the electron. So here we have a kind of potential energy for the electron in its ground state. This is the lowest energy. When it absorbs energy, it goes up to a higher energy state, more potential energy. But electrons are not going to stay in that position very long, right? So again, they don't want to be in a higher energy state. They actually prefer to be in a lower energy state. So what's going to happen is the electron is going to then release that energy that it absorbed and go back down to the lower energy state it was. So it's going to relax. We say this is relaxing. So the excited electron relaxes back down to ground state. In doing so, it loses that energy. So going from a high energy to a low energy, it's got to lose that energy. And it loses that energy often in the form of light. And so again, it's following the Aufbau principle, right? The Aufbau principle says electrons want to be in the lower or lowest energy possible, so they're going to fall back down. So again, person on the ladder, they might slip and fall, and as they fall, they're going back down towards the ground, losing gravitational potential energy. So this is analogous. And so here you can see in this picture, you've got energy level 2 and energy level 1. So the electron here went from ground state here, E1 is its ground state, and it goes up to E2, higher energy level because it absorbed energy. and then it comes back down, and when it does, it releases a photon of light. So remember, particles of light, we call those photons, and they have wavelengths, and the energy of the light, we can figure that out by multiplying this Planck's constant times the frequency of the light, which is the inverse of the wavelength. And so here's the equation down here. But the thing to keep in mind here is that the energy difference here between the two energy levels is the same as the energy in the light that's being released. So if you want to know what energy levels or how big of a gap here, you then measure the energy of the light, and you'll know how much of a gap between the energy levels the electron transitioned through. And so there's different ways to draw this same picture. So basically you want to make sure that you're showing if energy is coming in or out and which direction the electron is moving, right? So here, and you've got the Bohr model here, and you've got two orbits. And so in this picture, you have the electron moving from an inner orbit that is closer to the nucleus. So this is low energy, because remember, the closer you are to the nucleus, the lower your potential energy. So it's like being close to the Earth, right? Closer you are to the Earth, the lower your gravitational potential energy. But if you go to a higher energy level, this higher orbit, which is farther from the nucleus, so that indicates higher energy. So this electron here absorbs energy. So there's the energy going in. The electron jumps up to a higher energy state, so it gets excited. And there it is at a higher energy state because it absorbed energy. And then later on, very soon afterwards, the electron is going to relax back down to the lower energy state. And when it loses that energy, it releases that energy in the form of light. So the light then has a certain amount of energy. That energy of the light is equal to the gap that the electron moved between. And so that's going to indicate a certain wavelength, because wavelength and energy are related to each other. And again, we can use this picture here for the same idea. Here we have a lower energy state. Here we have a higher energy state. You can heat up the atoms, putting energy into the atoms, and so the electrons will pick up some of that energy. So they absorb the energy, going to a higher energy state, which is now the excited state. And then they relax back down to the lower energy state, releasing light. And again, that light, the energy of the light is going to have the same amount of energy that is the difference between the two energy states. And so that energy is going to be related to wavelength. Okay, so we can then, see the light that's emitted from these different substances. So the amount of energy that is given off by these substances is going to depend on the energy levels that the electron is falling from. We just saw that. So the energy level, how big of a gap there is, it means that the difference in energy is going to be larger. And if the electron jumps a larger distance from a high energy to low energy, then the photon of light emitted is going to have more energy, and therefore it's going to have a certain wavelength. And so here we can see in this picture that the amount of energy, so we have high energy down here, and we have low energy up here, and you could see the wavelength changing. So high energy is associated with very short wavelengths, and low energy is associated with longer wavelengths. So as we were talking about before, the larger the gap between the energy levels that the electron is jumping between, right? So if the electron falls from one energy level to a lower energy level, if that is a larger gap, that means the photon that's released is going to have more energy. And if it has more energy, then the wavelength is going to be smaller. If the gap is smaller, if the gap that the electron is falling between is smaller, then that means the light photon that's being released is going to have smaller energy and therefore longer wavelength. And so here in the middle, you could see this visible spectrum. This is the spectrum of light that we can actually see. Anything beyond that spectrum we can't see. So UV light, PET scans, gamma rays, we can't see those. Those are invisible to us. And even on this side, when they're longer, these are invisible because our eyes can only pick up wavelengths within this small band here. And the thing I want to point out here is that you could see here that the color of light is in a certain order. So red is on top, violet is on the bottom, and we'll talk about that in a moment. So here we have different series of light, and so the electron can jump from any level to any level, right? So here we have this small inner one that would be your n equals 1, that really tiny circle around the nucleus, right? So that's energy level number 1. And then this second one here is energy level number 2. This third one here is energy level number 3, energy level number 4, energy level number 5, and then we have 6 out here and 7. So we have 7 energy levels being represented here. And the electron can jump up to any one of these levels and fall back down to a lower level. So the electron can jump to this level, fall back down to this level, or it could jump up to this level, fall back down to this level. So you could see that there's different ways in which the electron can go down to a lower level. And as I was saying before, the larger the jump down by the electron, the more energy that's released, right? Because you got a larger gap between the energy levels. Larger gap means, larger difference in energy. And so that means if the electron jumps from way up here down to here, the energy is going to be that's released is more. And so the photon of light that's released is going to have higher energy and therefore lower wavelength. If you see down here, the electron jumps from this energy level down to this energy level, so it's got a smaller gap. So the light that's released from that electron, when it moves down to this lower energy level, is going to be smaller. So smaller energy means longer wavelengths. And so remember, the wavelength of light is associated with a particular color, right? So here in this series called the Balmer series, this is where we can see visible light. Now, these other series, the Lyman series and the Paskin series, Brackett series, and so on, these series also produce light, but a lot of the light that we see is not visible to us. So much of the rays, much of the light that's being released by these transitions are not visible to us, but this series is visible to us. And so what happens when these electrons release the light? Well, different elements have different numbers of electrons, and those electrons are filling in different energy levels. And the thing we have to understand is that as we put more electrons into a particular atom, right, or of a particular element, right, every time you put an electron into an atom, into a different energy levels, that additional electron causes the energy levels to change a little bit. So no element, no atom of a particular element is going to have the exact same energy levels as another atom of a different element. because different elements have different electrons, and the number of electrons causes the energy levels to change a little bit. So when you look at what energy is being absorbed or emitted by a particular element, only that element will produce those different waves of light, those different wavelengths of light. So this is like a fingerprint of an element. So just like we have fingerprints to identify different humans, and every human has a different fingerprint, so also the elements have different emission spectrums. They have different atomic spectra that identify that element and only that element. So hydrogen, you could see these bands of light by hydrogen. Only hydrogen will give those bands of light. So these are the bands of light or wavelengths of light that is emitted by hydrogen and hydrogen alone. So here we have all these bands of light from neon. You can see that there's only a few bands of light from hydrogen. Hydrogen only has one electron, so there's not as many transitions by the electron from one energy level to the other. But neon has more electrons, so there's many more transitions done by those electrons. And iron still has more bands of light because it has more electrons. But none of these bands of light in iron are going to be superimposed or match up with any of these bands in neon because the energy levels are different. They can be very close, but they're going to be slightly different. Okay, so the energy spectrum, so you can measure the exact wavelength, and when we get the light, so we're going to get the light from the atoms, we can then measure the exact wavelength of the light, and then that wavelength will tell us how big of an energy gap that electron fell from, right? So we know that as the electron falls from higher to lower, it releases a photon of light with a wavelength, and that wavelength is associated with the amount of energy lost by the electron, which is associated with how big that gap is. And so here we can see the rainbow of light, and as I was telling you before, the order of the colors tells you the energy. So red has low energy, purple has high energy, or indigo violet if you want to go that right way. So low energy is associated with longer wavelengths, and high energy is associated with shorter wavelengths. So as you go from red to purple, you are going from low to high energy. So purple light has higher energy than red light. So what that means is that if you find purple light being emitted from an atom, that means that the electron that gave off that light was relaxing or going through a different gap, a larger gap in its energy. So it fell down a larger gap and produced a higher energy light. So it lost more energy and produced that light. If you see red light, then the electron only lost a little bit of energy because it jumped down to a lower energy that was not as big of a gap between them. And so you can see that with orange, yellow, green, and blue. So the easy way to remember the order of the colors is by remembering Roy G. Biv. Think of that as someone's name. Roy is the first name, G is the middle initial, and Biv is the last name. So Roy, red, orange, yellow, G for green, and then Biv is blue, indigo, violet. Here they have purple, but indigo violet is often said as well. So how do we get these emission spectra? So there's two ways that you can get spectra. So wavelengths, what wavelengths does it give off, or which wavelengths does it absorb? So either way is used. So when we're looking at emission spectra, the way this works is we're looking at a hot gas. We're looking at the light that is absorbed or given off by that hot gas. So the light that's given off passes through a prism, and then as the light passes through a prism, different wavelengths of light are separated from each other based upon how quickly they can go through this prism, and different wavelengths of light can go more or less quickly through there, and so you get the bending of the light and they get separated here. And so this is an example of emission spectrum. So different light bands that are produced get passed through this prism and then they get separated here. So these are this would be an emission spectrum of whatever this hot gas is. Another way you could do it is through an absorption spectrum. And the way this is the opposite. The way this works is you have a light source again. And so this light source is producing all of the wavelengths of light. So all the different wavelengths of light are passing through this cold gas. Now we have a cold gas. This cold gas is now going to absorb certain wavelengths of light instead of emitting them. So most of the light is going to pass through this cold gas except for the ones that are absorbed by the gas. And so the light then passes through the prism, and then you get this more color, this spectrum of color. And what's going to be different here is that instead of having the bands of light show up, you're going to have dark spots show up where the bands of light should be, and they don't show up because that light was absorbed by the gas. So either way, we can identify what the element is, either by what wavelengths were absorbed or what wavelengths were emitted. And they are going to be the same wavelengths. It's just that one is showing you them as emitted and one is showing you them as absorbed. And so here's the example again. So here's what you would see from natural light or from a light bulb. So you have a light bulb giving off all the wavelengths of light. Those wavelengths of light pass through the prism and you get this rainbow, this continuous spectrum. There's no gaps. It's all rainbow all together. That would be normal. The emission spectrum, as I said, you have the hot gas, and the hot gas is emitting certain wavelengths of light. Those certain wavelengths of light are passed through a prism and then they are separated, and you can see the bands of light show up here on the spectrum. You'll notice that most of it is dark because this hot gas is not emitting all of the wavelengths of light. It's only emitting a few. And so only the light that is emitted is being shown up. And so this will help identify what the element is. So this is what happens when we do a lab. Now here, when we're looking at the sun, when we get an emission spectrum, the light source that's emitting all the wavelengths of light passes through a cold gas. Some of those wavelengths of light are going to be absorbed. So the same wavelengths of light that were emitted here are now going to be absorbed here. And so the rest of the light that passes through goes through the prism. And then you can see that you can see the colors of light here. And then the ones that are missing are the exact ones that are emitted here, but they're missing here because the cold gas absorbed them. So this is an absorption spectrum. And this is what happens in the stars, right? So normally we have absorption spectrum. So what about flame tests? So we can do flame tests in a lab, and we can say, from the flame test, we can identify the different colors, and different colors will identify different elements in the substance. And so here you can see that you got lithium chloride, sodium chloride, potassium chloride, rubidium chloride. They're all chlorides, but they're producing different colors. So if it was the chloride that was producing the color, they should be all the same color, but they don't have the same color. So it must be the metal ion here, the first ion, lithium, sodium, potassium. Those are the ions that are producing the color. So here you can see lithium producing reddish color. Here sodium is producing a bright yellow color. Potassium, a sort of magenta color, if you will. Calcium down here is producing a really bright orange color, and so on. So you can identify what element there is by the color that you see, because again, different elements produce different wavelengths of light and therefore different colors. And so this is where your fireworks come in. different fireworks produce different colors because they have different elements mixed in with the firework itself. So if you see blue, that means copper chloride was put in there, or maybe it was copper, some other copper compound. Copper is a typical color that a typical element that gives blue. If you have sodium in there, then you would see a yellow color. So yellow is indicative of sodium being in the firework. Calcium chloride, we saw calcium give an orange color. So if you see orange in your firework, then that indicates that calcium was in there. So this is why different fireworks give you different colors, and you can get a mixture of colors because you have a mixture of different elements in the fireworks. And once again, we can see here that we have these different emission spectra, and these are the fingerprints of different elements. So just like we humans have different fingerprints and we can be identified by our fingerprints, each element has a different spectrum with different bands of light, different wavelengths of light that show up, and these spectra will identify the element coming from a particular sun. So we can identify what elements are in different stars by analyzing the different wavelengths that come in. And if those wavelengths line up with particular elements, then we know that in that particular sun or star, we have those elements. And here again is an example of an absorption spectrum. So same thing. You can see here that you have a rainbow, but instead of seeing bands of light, you see dark bands. You see bands that have no light, and that's because they were absorbed by the element. And so in this case, we're looking for dark spots. And if those dark spots line up where light should be for that particular element, then we identify that element as being hydrogen or helium, depending on where we see those dark bands. So again, here, this is where the absorption is occurring. And so we don't see the light because it's been absorbed by the element in that star or sun. And again, here's the different bands of light. This is different spectra that we see from different stars. Here's the spectrum from the Betelgeuse. Yes, there is a star called Betelgeuse. And so you can see the bands of light, and you can see the dark bands where there is no light, so you can identify what elements are in that star. Here, Rigel, this is another absorption spectrum for that star. And so we can use these to identify what elements are there. And so that's it for this video. I hope you enjoyed this video. I hope this was educational. If you like this video, please hit that like button, share this video, subscribe to my channel, hit that notification bell. Let me know what you think in the comments. Ask questions. I love questions. Thanks for joining me. Have a great day.